So, okay, I will begin the talk while it begins. So, we used to be a research group at INRIA. We started a group in 2008 to develop algorithms for molecular modeling. Inspired by people like you, Eric Drexler in particular, but many of you. And the idea was that if we wanted to save the world and help everyone, we couldn't do it alone because it's so rich, it's so complex. Like you have to study biology, physics, chemistry, quantum mechanics, high performance computing. So nobody can do it all. And so we had to make an open platform to do this. And so we did it with a computer science approach. And we spent a lot of time, a lot of money, a lot of European money to do this. Like, I don't know if you know the ERC programs. Restore, no. And so it ended up being called Samson, for software for adaptive modeling and simulation of nanosystems. It works in French as well. And the idea was, again, to make... Oh. Whoa. Well, no. Okay, I should hide some stuff. Yes. Okay, so again, the idea was to make it open. And because of this, we created Samson and a software development kit called the Samson SDK that you can use to create extensions. So the goal is for us to help you integrate your expertise into the platform. And so you have this marketplace with extensions, and depending on what you like to do, you can add different extensions. So if you do drug design, you'll add extensions for protein ligand docking. If you do visualization and animation, you'll use this extension that's actually included. You can do cloud simulation using GROMACS, protein-protein docking, etc., etc. But again, it's extensible. And so you can write your own extensions either in C++ or in Python. So I'm going to show it. Oh, and in the same spirit, we actually make it possible to share documents. So bits. Sorry, Apple Watch. It's also possible to share documents, a bit like in the spirit of a nanobase. And again, because Samson is extensible, the file format also is extensible, and so it's a computational file format. If you want, like to read some parts of the format, you're going to use some extensions. So here's how it works. So, obviously, one thing that you would like to do is visualize. I'm going to have trouble. So the first thing that you could do is, for example, download a structure. Oh, that's embarrassing. Thank you very much. Thank you. You were actually one of the inspiration with Kendo. Very. Thank you. So one of the first things you do is visualize, of course. So I'm going to do a transition with the previous presentation by just downloading a protein designed by the Baker Group. So one thing that you could do, thank you very much. One thing that you could do is download structures, visualize, add lots of visual representations, and you can even create new visual representations just to make it easier to interpret your own work. Okay. So one thing that's typical is, let's say, visualize in the PDB style, so in one click you can do this. But of course that's obvious, and many programs do this. So I'm just going to reset the visualization, add back shadows. Then something maybe a bit less common that you can do is animate things. So I'm going to open this animation, and here if I double click this presentation, so you can make presentations with slides and animations and move everything. So I'm going to click on here, and you can change the time frame. So you see that here you have a docking animation in the HIV protease, and you could change the parameters of the animation, make something dock sooner or later, these type of things. Change the positions of the camera, to control your visualization. So visualization, animation, communication. Then what you can do also is construct, of course. So you can do it in multiple ways. Either you use fragments, so atoms, and you minimize at the same time, because it's very important to get a feedback as soon as possible. So for example, here the minimization helps me construct something, and I can just move things in order to have immediate feedback on the plausibility of the structure, which you could not do. I mean, if I don't minimize, I'm just going to very rapidly produce an unrealistic structure. Okay, so obviously you want simulation as soon as possible. So you can have multiple building blocks like this, and you can actually add your own building blocks, and you can also do some type of procedural generation to construct things. So for example, I could use a nanotube creator to just build a nanotube and then use some editors to, let's say, deform it. And I can use the same type of algorithms on a protein. So let's say I open this. I'm sorry, I keep moving. If I open this, for example, so just simple protein, I could also use the same type of algorithms to deform them. So use control points and maybe move a loop, unfold a helix, refold it, etc., etc. Okay. So, of course, if you build more and more complex objects, you want to use potentially advanced simulation methods. So, for example, reactive simulation methods. So here I'm going to apply a simulator. So sorry, Jonathan, but you need virtual methods. When you have an open platform, you cannot optimize everything. So you have to delegate some function calls. So here I'm adding a simulator called the Brenner force field, and you have an abstract representation where you have a dynamical system. So you have some things which contains the description of the degrees of freedom in the system. Then you have an interaction model, something which associates an energy function to degrees of freedom, like the two parts of the Hamiltonian, if you want. And then I can just start this interactive simulation. And so here it's probably going to unfold at some point, unless it created some bonds. But here what I can do is just edit the structure, break some bonds and form new ones, and have some immediate feedback on the structure. Like for example here, as you know, soccer ball alternates pentagons and hexagons, and this is what is curved, and so here I'm observing that there is a curvature created. So you have also extensions like this for DNA. If I just go back here, Elisa Delano developed Adenita inside Samson. So it works like this. I'm really not a specialist, so I'm just going to show it very briefly. Here, let's say I want to create this tetrahedron. I'm just going to click like here. Sorry. And then I'll have this structure that I could take, move, etc., etc., edit, move, copy, paste. So this is one of the things. Again, the spirit is that we want to be able to integrate everything and combine everything. And finally, sometimes, of course, you want to do long simulation, like, for example, one-day simulation on the GPU. So let's say you can do that using GROMACS that we integrated. So let's say I load this protein structure again. I'm going to use GROMACS. So typically the first step that you need to do is prepare the system. So I'm just going to say, well, this is my system. I want a simulation box of 6 nanometers. I click prepare. Then I'm going to minimize the system to prevent clashes. So these 2 steps, so I say start from the previous step, minimize. So these 2 steps are run on the computer, but then potentially you want to develop computational services in the cloud. So in the next step, I'm going to do it in the cloud. So I go to the equilibrate step. I just, again, I click the magic wand to start from the previous step, and I click equilibrate in the cloud. So here it connects to the cloud and says, well, you have this choice of machines for different credits. I select this one. Then there is a security by Samson, because an extension is trying to take your computing credits. So I just say, okay, it's me, I really want to do this job. I have a new job created. It's initializing, so it's sending all the input files necessary to do the calculations to the cloud. And I can monitor this job. And of course, you can run many experiments in parallel, because you can just create them, potentially programmatically, and launch simulation jobs. So these type of things. So here is, once it's initialized, it's asking me if I want to start it, so I just say yes. And now it's going to move to the running step, and then I'm going to be able to download files, so I can show you with the previous job I ran. Then you receive a notification here. I downloaded the files already from the cloud. Okay. So again, this is very, very general. The core is very stupid and abstract, and all the intelligence is in the extensions. And that's why I would like to discuss with you to integrate stuff, collaborate, because I think we can help each other by integrating and working in a single platform. So thank you very much. And thank you very much for the holding of the mic. So, technical questions immediately. So, obviously it's going to depend on the force field. So you need a good force field. So currently you have some force fields integrated. And so with transition metals, for now, we wouldn't have a way to simulate it. So we would have to integrate an existing force field that's able to realistically simulate transition metals, like let's say quantum methods. Or if you work in programming force fields, you can actually program it inside here, so you don't have to reinvent the wheel of the parsers, the visualization, etc., etc. Something I didn't say actually is that very rapidly we have extensions that help you write extensions. So, and it's also possible to write extensions in Python. So for example, let's say it's closed since it rebooted. So let's say I have this little script here, Python script. So here it creates a little window with a button, move atoms. And when you click the button, it calls this function. And this function, what it does is it finds all the atoms in the document. And for each atom, it adds 1 angstrom on the x coordinate. And you have these two instructions, begin holding and end holding, to store incremental modifications to the document. So if I just drag and drop. So let's say I add atoms here. I'm doing a drag and drop of this. No, it's fine. Thank you very much. A drag and drop in the window. So the first time it takes a few seconds to initialize Python scripting. So everything can be scripted in Python. So now I have this new interface that was created. And if I click and move atoms, it translates the atoms. Okay, with this, so you can very rapidly develop prototypes of codes to develop extensions. Okay, and because I added these begin holding and end holding, it's user friendly, and you have this move atoms in the history stack. Okay, so there's lots and lots and lots of hidden software engineering practices like design patterns and stuff that you should not be bored about, because you need to do science and save the world.
What's the limit? I mean, in terms of multiple size, which you can still render?
Render? We render millions of atoms. Like the HIV capsid, actually I think it's visible on the website here. Yeah, you can render millions of atoms because we use shaders and stuff. Plus, anyway, you can have what you saw on the Adenita is actually a coarse grain representation with tubes, so you can just use coarse grain models. Yeah.
Thank you. All right.
Thank you.